Let's discuss November 2025 IGCSE Chemistry first paper, 1C paper. Okay, first question is says that the diagram shows how particles are arranged in the three states of matter. So we can clearly see that they have given a solid phase, liquid phase, and gaseous phase. Give the names of the changes of state labeled X, Y, and Z. So we can see that in X, it's simply a solid is turned into a liquid. A solid turns to liquid. We know what is that process. It's called melting. Second one, they're asking what is Y. A liquid turns to gas. Liquid turns to gas. We can call it evaporation or we can call it boiling. So in both process, liquid will turn into gas. So it will be boiling. Then the last one, process Z. A solid directly turns to a gas, skipping the liquid phase. When a solid directly turns to a gas, skipping the liquid phase, we call that process a sublimation. So we have the answers. X is melting, Y is boiling, and Z is sublimation. So this is a very easy question. Then they are saying that water vapor condensed to form water. Give the equation for this change of states, include the state symbol. They say that water, okay, so water, chemical formula we know it, is H2O. Water vapor, so that means H2O in a gaseous phase. Condenses, okay, forming what? Forming water. So when a gas condenses, we know that it forms a liquid, because water in the normal temperature, in the room temperature, is a liquid. So what is the equation we are having here is H2O gas forming H2O liquid. Then part C, they are saying that describe how particles are arranged different in solid and gases. Right, we had this phases here. We have what we can see in this solid phase. We can see that in this solid phase, particles are regularly arranged. So you can see that their arrangement is very regular. You can see the pattern. And they are packed, closely packed with each other. So you can see they are closely packed. But when you talk about gaseous phase, they have want us to compare solid phase with gases. In gaseous phase, you don't have the regular arrangement. We have random arrangement. And we can see that there's a huge space between particles. Therefore, we can't use the word that closely packed. We can say that widely spaced. So when you're writing the answer for this one, we can say the first point, solid particles have a regular arrangement. Regular arrangement and while gas have randomly arranged. While gas have randomly arranged particles. They are talking about 2 points, so we talk about the arrangement. So then we can write solid particles are tightly packed. While gas particles widely spaced. So we just told their differences. Solid particles have regular arrangement, but gas have randomly arrangement. Solid particles are tightly packed, where gaseous particles are widely spaced. So from that we got both marks. So when there's a question which is a little bit confusing only, we'll go for the marking scheme, because otherwise these questions are very straightforward questions and the answers are also straightforward. Question number 2. The box gives the names of some gases in the atmosphere. So let's see what are the gases we have. We have argon. Argon is a noble gas. So therefore they stay as monoatomic gaseous particles. Carbon dioxide is formula is CO2. Nitrogen formula is N2. Between two nitrogen atoms there's a triple bond. Oxygen is O2. Between two oxygen atoms there's a double bond. Water vapor means gaseous water molecules. So these are the things we have. First question they're asking, identify the gas with a molecule that contains a triple bond. Yes, we know that the gas which has a molecule which contains a triple bond, that is nitrogen. So our answer for this question is nitrogen. In the second question they're asking, identify the gas in the atmosphere that exists as individual atoms. So we can clearly see that carbon dioxide 3 atoms together. Water vapor also 3 atoms together is a molecule. Oxygen also 2 atoms together, diatomic molecule. Nitrogen also 2 atoms together, but argon is a noble gas. It has only one monoatomic gases. So therefore our answer for this one is argon. Identify the gas needed for combustion reactions. We know that combustion means a reaction of a substance with atmospheric oxygen. That means it's a reaction between oxygen. They're asking, identify the gas needed for combustion. Okay, we know what is the gas required for combustion. It's the oxygen gas. So this is also a straightforward question. So no need to worry about it. We can move forward. Explain how carbon dioxide can be formed from copper carbonate. Right? From copper carbonate, we can get carbon dioxide in two ways. One method is, I'll just discuss the methods here. One is you can simply heat copper carbonate. So when you heat copper carbonate, it will decompose, forming copper oxide, which is solid, plus carbon dioxide gas. That's the first method. Second method, you can add an acid to copper carbonate. Let's assume for copper carbonate, I can add dilute hydrochloric acid. Let's assume I am adding HCl. When I add HCl, what we will get here is, you get the salt of copper chloride. When a carbonate reacts with acid, you get salt plus carbon dioxide gas plus water. Okay. From that also you can get carbon dioxide from copper carbonate. Okay, now we need to write an answer now. So we'll write the answer. I'll take this heating one, right? So I will write here heat copper carbonate until it decomposes. Giving carbon dioxide gas. Right, that's the thing. Okay, so heat copper carbonate until it decomposes, giving carbon dioxide gas. Okay, let's see. So the marking scheme says that, okay, we can use both ways. You can see both the techniques, either heating or either adding an acid. So we wrote the heating part, so we mentioned about heat, we get the first mark. And until it decomposes, that's the second mark. So you get full mark for this question. Okay, no issue with that one. Right, let's move to the next question. A student used this apparatus to calculate the percentage of oxygen in the sample of air. Okay, we have a sample of air. Here we have the sample of air. So this is the column of air is here, right? So that's the sample of air. Right. So then they are telling us initial height of the column of air. So initial height is there. So that means initial height means from here up to here, this level, no? Yeah. So we have the initial height. What is the initial height? 93 millimeters. Okay, we have the initial height. Then what we do here is then we have, I'll redraw this one. Okay, we have the beaker. And we have that boiling point, boiling tube, which is inverted. Inside that one, we have the iron wool. So what will happen when you have wet iron wool here? Iron will cause rusting. So this will undergo rusting. What is rusting? Will rust. Rusting means reaction with oxygen. So that means when it rusts, it will consume oxygen. Okay, it will consume oxygen. When it consumes oxygen, now initial my liquid level was here now. So I just redraw it. So this is, and this one is the other. This is the initial liquid level. Okay, what will happen when it is rust? It will take oxygen now. So there will be a vacuum. Whatever the oxygen volume there, now they are not there. Now let's take, we had oxygen up to here. This is the volume of oxygen we had in this sample. So this is the volume of oxygen. Okay, let's assume this height of oxygen volume is x. So we call it, this is x, right? So in this diagram, this is the value of x. Now what will happen when the oxygen is removed? Our liquid level will rise up. So what will happen? This liquid level will rise up. Up to what point? To cover the volume where you had oxygen. Now the new liquid level is here. That's what you're going to observe, right? So it rises up to cover the, now when you remove the oxygen, there will be a vacuum now. To replace that vacuum, the liquid level, water level will rise up. Okay. Now we know final height of the air column. They say that after we do that one, the final height of the air column, that means this part from here to here. Now this final height is not 93. 93 was the initial, final height is 77. Okay, 77 is the final height. Okay, now I have these values. Let's see what we can do here. The first question asks, use the student result to calculate the percentage of oxygen in the sample. So I'll do that calculation in the same diagram here, right? Because then you can understand. So we want to find the percentage of oxygen here. To find the percentage of oxygen, we have to use this equation. So percentage of oxygen equals first you have to take volume of oxygen divide by total volume into 100. Right, let's see how we are going to find this one. So percentage of oxygen equals volume of O2. Volume of O2, can you remember this value of x? No, this value x tells us the how much height of volume. So you might be thinking its height is not volume, no. But we know that volume means cross section times height. So that means x times, if you take cross section, let's assume it is a, and that's the volume, divide by total volume. What is total volume? 93 is the height. 93 is the height times cross section. What is a cross section? Again, it's a. So this a and a will cancel out, no? So therefore you don't need to use the volumes. You can simply use the height of the column. So height of the oxygen column is x. Here we have it. Height of the total column is 93. The total air column into 100. When I do this calculation, I will get the value of percentage of oxygen. Now how do I find x? That's so simple. So when I take this final, so when I take this final diagram, so I'll only use the final diagram for our calculation. Now we are here, so I'll just erase this part. So I just put everything on the same diagram now. Right, now I have the value of x. Right, now I need the total volume. Total volume also we can mark it here. So we know that height from here to the bottom at the beginning, it was 93. Okay, now can you see when you put all these three things in the one diagram, you can see that 93 equals, from this side, from the other side when you look at it, is equal 77 plus x, isn't it? So 77 plus x equals 93. So from that I will be able to find what is the x. X is the height of the oxygen. So when you do that one, x is 16. So x equals simply 93 minus 77. So x equals, here if I write it here, it's 93 minus 77. Here you get 16. And now I have to substitute it here. So it's simply 16 divided by 93 into 100. When you do this calculation, you get the answer as 17%. Okay, that's the percentage of oxygen in this column. Now we have a problem. According to the things that we have learned, it says here the percentage of oxygen in air is approximately 21%. We know that is 21%, but here is 17%. That means we did not let all the oxygen to get consumed. That means there is some amount of oxygen remain here without reacting, without the water level going up. Why is that? Because the reason is, I think the rusting is incomplete. We know that rusting is a very slow process. It takes many months, years to take place. Now here we did only left this setup for 1 week. They're asking, suggest an improvement to the method that would increase the accuracy of this student's result. So what we can do here is leave the experiment for longer period. So when you leave the experiment for a longer period than 1 week, what will happen? Then rusting will complete. Or otherwise what you can do is, we can keep on observing. Leave it for 2 weeks, leave it for 3 weeks. There will be one point, this liquid level will rise up. Our liquid level will rise up and will stop rising up. So it will end in one point. It will keep on going up and going up, and in one point it stops. When you stop in that point, you know that okay, that's the volume that oxygen, all the oxygen has been used up. So this remaining one shows that there's no more oxygen is left. If there's no any more oxygen left there, the liquid level will keep on rising up because rusting will consuming oxygen. If the liquid stops there, that means, what does it mean? There are no more oxygen to react. That's what happens there. Leave the experiment for longer period. So from that, we can improve the accuracy of this experiment. Okay. So yes, we have the answers for question number 2 also. Now let's move to question number 3. So these are straightforward questions. So therefore, no need to prefer the marking scheme because they are easy questions. Right. This question is about atomic structure and the periodic table. The diagram shows an atom of an element. Okay, they are showing an atom. Right. Now the first question asking, use the diagram to answer this question. Which particle is a proton? We know that proton, so you can see 2 parts here. In the middle part, we call it nucleus. Around it, we have energy level. Proton is a positively charged particle which we can find in the nucleus. So you can see that there's a positive charged particle and it is labeled as X. So that's the proton. So therefore answer for our question number 1 is B. Question number 2. Which particle have a relative charge of 0? So we know that in the nucleus there's another particle which doesn't have any charge. We call it neutron. So now we know that X is proton. And we know that, alright, then the neutral particle, there's no charge. You can see they have labeled it as W. We know that W is the neutron and which has no charge, its charge is 0. So answer for question number 2 is A. Name the part of the atom labeled Z. So this is neutron and this is proton. So then Z is pointing for this whole circle, the big part. That means they are talking about the nucleus. So label the part Z. Z should be nucleus. Alright, that's the part we have. Right. Then we'll move to next part. What is the group number of this element? So remember, group number of an element is equal to the number of electrons you can find in the outermost shell. This is the outermost shell. Outermost shell or outermost energy level. In the outermost energy level, we can have 2 and another one. 3 electrons there. That's equal to the group number of the element. So since we have 3 electrons in the outermost shell, the group number of this element is group 3. So answer for question number 4 is B, which is group 3. What is the period number of this element? Question number 5, they are asking what is the period number of this element? Period number equals number of energy levels. So here we have the first energy level and you have the second energy level. If you have 2 energy levels, your period number is 2. If you have 3 energy levels, your period number is 3. So since this one has only 2 energy levels, its period number is 2. Alright. So period number of this element is 2. That means answer for this question is A. Question number 5. Question number 6. Give the chemical symbol of this element. So we can see that in this element we have 1, 2, 3, 4, 5. 5 protons. 5 protons means that's equal to the atomic number of the element. So if you look at the period table, if you have 1 proton is hydrogen, 2 protons is helium, 3 protons is lithium, 4 protons is beryllium, 5 protons means is boron. So therefore from the atomic number we can identify what is this element. So the element we have here is boron. So give the chemical symbol of this element. It's simple. It's simply capital B, letter B, which is boron. Part B. State what type of particle is formed when the atom loses its outer shell electrons. Okay, when you remove an electron from the outer shell, so let's take this electron is gone. So in the nucleus we have 1, 2, 3, 4, 5. 5 protons. 1 proton is +1, so 5 of them is +5. But electrons we have is when you remove the outermost one of the electron, 1, 2, 3, 4. 4 electron, that means -4. So +4 minus +5 -4. So when you have +5 and -4, what comes outside? +1 comes outside. So this is a positive ion. So you can write it as positive ion. In chemistry, for positive ion, we use one single word. We call it cation. Now, if you have Negative ion, we call it anion. So here is a positive ion, or we can call it cation. Okay, now we are coming to the part C. The table shows the atomic number and the relative atomic mass of one decimal place of elements in period of the periodic table. Okay, we have element, atomic number, relative atomic mass. On the grid, add an appropriate scale to y-axis starting from 6. Okay, that means they are expecting us to draw a graph. Okay, atomic number is given, so that is on the y-axis. So x-axis, we have to do it is start from 6 and goes up to 20. How many boxes we have? Let's go one by one. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 20. What is the highest number we have here? Is 20. Yeah, that's better. So we can call it, this is 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, now we have to mark these points. Now let's see how we are going to mark these points. Plot the data on the grid. Do not join the points. That means they don't want us to draw a graph. So when the atomic number 3 is 6.9, 6.9 means one box is 1, 2, 3, 4, 5. Okay, only 5 boxes are there. So that means 1 point means 0.2. So 6.9 means 6.2, 6.4, 6.6, 6.8 are right somewhere here in the middle. That's the first point, 6.9. Then we have 9.0. When it is 4 is 9.0. Okay. When it is 5 is 10.8. 10.8. 1, 2, 3, 4. Yeah, here. When it is 6 is 12. 6 is 12. When it is 7, it's 14. When it is 8, it's 16. When it is 9, it's 19. Okay, so it's here. When it is 10, it's 20.2. 20.2 is here. So you can do it, right? Because I have to, like, it's really hard for me. So you can see this 19 is a little bit going up. So I'll try to fix that one. But you can, so you can do it properly. So it's 19, right? Exactly. Okay. So these are things you have to remember, right? When you are drawing a graph, so when it is 10 is 20.2. So it should be, I just small mistake is not here. It is 10, it is 20.2. All right, somewhere here. Yes. Yes, 8. Yes, now it's fine. Okay. Now one thing you have to remember is when you're drawing graph, so these are the things. So even your graph is right or wrong, there's a specific point they give marks, right? So first mark they will focus on whether you have labeled the axis clearly. That's one thing they will check. So they will check whether you have put the two axes. So whether this axis and this axis. And if there's a unit for each axis, whether you have mentioned the unit. Now here there's no unit, but usually if there's a unit, you have to mention there. And each and every point they will look very carefully, right? For each and every point. So therefore when you're marking these points, you have to be very careful. And when you're making this graph, you can use pen for mark the axis and these numbers. Only inside the graph you can use pencil, right? But the axis you have to use the pen. And the next thing is, okay, so you have to use those two. And the next thing is, if they ask you to, make this like this. Take here, I have to use the axis, right? Scale for this axis. Whenever you create the scale for axis, at least it should cover more than 50% of the graph paper. It should go beyond 50% of the graph paper. So in our graph, yes, it has gone beyond the 50% of the graph paper. Those are the points you have to be careful when you are drawing the graph, right? So this is fine. So we got full mark for this one. In the next question, they are saying that identify the relationship between relative atomic mass and atomic number for this element in this period. This is one mistake most of the students do. Now remember, they are saying that do not join the points. Why? Because this is not a linear relation. Can you see? It's not a straight line. So therefore, you can't say that they are directly proportional to each other. If you get a straight line, then you can say that they are directly proportional to each other. But here you can't do that. So therefore, but you can see one thing. When the atomic number increases, relative atomic mass also increases. Therefore, what you can tell is something like this. Then you can tell that when the relative atomic mass, when the atomic number increases, relative atomic mass also increases. You can write simple like that. You can say that as the atomic number increases, so does the relative atomic mass. That also increases. You can write something like that. Okay. Now we'll go for question number yes. Positive correlation between the relative atomic mass and the atomic number. As the atomic number increases, so does the relative atomic mass. So that's the question answer we wrote. But can you see here? Reject directly proportional because it's not directly proportional because it's not a straight line in that graph. Okay. Now let's go for question number 4. Right. Question number 4 says the question is about ammonium chloride. Okay. Draw a diagram to show the arrangement of the electrons in a chloride ion. Okay, now here remember this one, they are talking about chloride ion. Okay, first we'll draw chlorine atom. So if I draw the chlorine atom, it has 17 electrons, so it will be 2, 8, 7. So if I draw the chlorine atom, so we have the nucleus in the middle. Okay. Then we have electrons. Okay, so what are we? You have the electrons. Electrons you can find in the energy level. So we have the first energy level, we have the second energy level, we have the third energy level. Okay, so first energy level you have 2 electrons. 1, 2. Second energy level we have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. In the third energy level we have 7 electrons. 1, 2, 3, 4, 5, 6, 7. But here they are not talking about chlorine atom, they are talking about chloride ion. Here chloride ion. So chloride ion means an atom gains an extra electron. So that means to make the chlorine to chloride, what you have to do is you have to give 1 extra electron. When you give 1 electron, okay, now we get this extra electron. So this is the chloride ion. So it will get the negative charge. So now we do the electron arrangement of the chloride ion. So we get full mark for this one. Right. Now we'll go for next one. 2 beakers are unlabeled. One beaker contains solution of ammonium chloride and the other beaker contains solution of ammonium sulfate. Describe tests that can be carried to confirm that one beaker contains ammonium chloride and the other beaker contains ammonium sulfate. That means they expect us to distinguish ammonium chloride from ammonium sulfate. Ammonium chloride is made out of ammonium ion and Cl minus chloride ion. We just draw the diagram of chloride ion, right? Ammonium sulfate is made out of, again, ammonium ions and sulfate ions. Okay, now we can use one thing to distinguish these two. What is that? Ammonium, because ammonium ion is common in both places. I forgot about ammonium ion. So that means only way I can distinguish them. With ammonium chloride, I have to do a test for chloride ion. For ammonium sulfate, I have to do a test for sulfate. Okay, let's see how we can do this test. What is the test for chloride ion? What is the test for sulfate ion? Test for chloride ion is, first you have to add dilute HNO3. Why? Dilute HNO3 is added to remove, if there are carbonate ion in the solution, we can remove them as carbon dioxide, because these carbonate ions disturb our observation. Why do we have carbonate ion in each and every aqueous solution? Because carbon dioxide gas in our atmosphere can dissolve there. So then after you remove the carbonate ion, now we have the halide ion. When you add silver nitrate, if it is chloride ion, you get silver chloride white precipitate. That's the test for chloride ion. What is the test for sulfate ion? For sulfate ion, first you have to add dilute acid like dilute HCl, again to remove the carbonate ion. Now you have the sulfate ion alone. Add barium chloride, then you get barium sulfate white precipitate. So now we know the test for chloride and test for sulfate. Now we'll use that one to write our answer. Two beakers unlabeled. Describe tests that can be carried out to confirm that one beaker contains ammonium chloride and the other beaker contains ammonium sulfate. Okay, first test is, we are going to do add nitric acid to ammonium chloride and then add silver nitrate solution, aqueous solution. White precipitate is formed. Will form, confirming Cl minus ion, chloride ion. Okay, that's how we can identify ammonium chloride. Right. Then we have to do something for sulfate ion. For sulfate ion, we are going to add HCl, add hydrochloric acid to ammonium sulfate, NH4, twice SO4, that's ammonium sulfate. And then if you don't know this formula, you can simply write the word, right? Ammonium sulfate. So if you know the formula, if you write the formula, it makes the answering speed faster, right? So ammonium sulfate and then add barium chloride solution. Then what will happen? Again, you get a white precipitate. White precipitate will form confirming sulfate ion. Okay, That's how we get the answer. So let's see the marking scheme. Add nitric acid. So we have the first mark. Add silver nitrate solution. Second mark. White precipitate formed. Third mark. Add nitric acid or hydrochloric acid. Fourth mark. Add barium chloride. Fifth mark. White precipitate forms. Sixth mark. So you get full mark for this question. Right, no worries. Now let's go for part C. A student draws to show the formation of solid ammonium chloride in a glass tube. Right. Explain the mistake in the student's diagram. Okay, this is a very common question. It comes like many years. So the same question comes again and again. Let's see about this one. So here we have ammonia solution. So ammonia solution means when it evaporates, it will produce ammonia gaseous molecules. And here concentrated hydrochloric acid. Concentrated hydrochloric acid gives you HCl gaseous molecules. Okay. What is the molecular weight of ammonia? We know that nitrogen is 14. Hydrogen is 1. There are 3 hydrogens. So 14 plus 3 is 17. And if you say hydrogen chloride, we know that hydrogen is 1. Chlorine is 35.5. If you look at the periodic table, so it's 36.5. Molecular weight of HCl is 36.5. So this is heavy. HCl is heavy. So when it is heavy, now can you see that during this formation of ammonium chloride, ammonia has only moved this distance, but HCl has moved from here to here. So usually heavy molecules should travel less distance. No, lighter one can go more further distance. It can move fast, lighter molecules. That's the mistake student has done. According to the real scenario, this ring ammonium chloride should appear somewhere here, very close to HCl. Why is that? Because HCl can't move further distance. Only ammonia can move further distance. Explain the mistake in the student diagram. The mistake he has done is the ammonium chloride. You can write the word, or if you know the formula, you can write it. So I'm just using ammonium chloride should form closer to the HCl soaked cotton wool. Now we are right why. The reason that is HCl molecule is heavy and moves slowly. Right, from that we can confirm why this happens like this. Okay, let's see the marking scheme point. Yes, marking scheme says that ammonium chloride should be closer to the hydrochloric acid, yes, close to HCl, so cotton wool. Why? As the hydrogen chloride has a higher relative molecular mass, hydrogen chloride has a higher one, so therefore it moves slowly. So we say that HCl molecule is heavy, so it moves slowly. Yes, so heavy molecule, higher relative formula mass. So higher MR. Yes, I think it's better if we write. So yes, I have made a mistake. Rather than saying heavy, it's better if you do this calculation and show it in your answer, right? So yes, so it's better. So you can add that part because I think that's the best part. So you can say that molecular weight of ammonia is 17 and molecular weight of HCl is 36.5. It's better if you include this part, then the answer is very complete. Then you can say that it's heavy. So you can show that its molecular weight is higher because they say that as hydrogen chloride has a higher relative molecular mass, relative formula mass. So they are expecting that one, right? So rather than just says it's heavy, right? So therefore that's the perfect answer. So then only you get 3 marks. 1, 2, 3 marks. Yes, I have written that answer incomplete. I might get 2 marks based on the scenario. So we have to be careful when you're writing the answers for these questions. Okay, let's move to next one. Complete the equation for the reaction in the glass tube by adding state symbols. Okay, complete the equation for the reaction in the glass tube by adding state symbols. So we know that ammonia is a gas here, and HCl is also gas, and ammonium chloride is a solid. It's formed here. So these are gas and solid. That's a straightforward question. So it's easy answer. Okay, now let's go for this one. Question number 5. This question is about displacement reaction. A student used this method to investigate what happens when excess metal is added to a solution of copper sulfate. Okay, now we'll mark the things. It's excess metal, right? And the solution is copper sulfate. So we have copper sulfate solution. We are adding metals in excess. This is pour some copper sulfate solution into polystyrene cup and record the temperature. Why do we use polystyrene cup? Why anything else? This polystyrene cup, you can call it like a rigiform cup or something. So the reason why we are doing this is this polystyrene cup is in heat insulators. Heat insulators means through these walls of this polystyrene cup is very hard to heat to go outside or outside heat to come inside. So therefore whatever the heat produced inside this cup, preserve there. But if you have something else, like take you have a glass cup, what will happen? Heat can easily go outside or outside heat can come inside. But here polystyrene is a good heat insulator. That's why we use this polystyrene cup. Add excess metal W to the polystyrene cup, and now in polystyrene cup we have copper sulfate solution. And we stir the mixture. Why we stir it? To make sure heat distribution is even, plus there will be rate of the reaction will be faster, because we want to finish this experiments faster, then we can move to the next one. Record the maximum temperature reached. Calculate the temperature increase of the solution. So what they did was they see how much temperature has goes up. The student repeat the method for metal X, Y and Z. They did same thing for metal W as well as metal X, Y and Z. OC. For each metal, the student record 3 sets of results. Okay, he get 3 readings because it's better to repeat the experiment. If you do one mistake in one experiment, you can find it out in the second one. Give a reason why the student could not use copper carbonate instead of copper sulfate. For that, we should understand we were talking about formation of salts. When you talk about preparation of salts in IGCSE syllabus, these are the 6 rules you have to remember. First rule is all sodium, potassium and ammonium compounds are soluble. All nitrates are soluble. Most common chlorides are soluble except lead and silver chlorides. Most common sulfates are soluble except lead and barium sulfate and silver and calcium. Most common carbonates are insoluble. Most of the common carbonates are insoluble except sodium, potassium and ammonium carbonates. So carbonates are insoluble but sulfates are soluble. Now they're asking a question from us. Why do we use copper sulfate, not copper carbonate? Now we know the answer. Copper carbonate is insoluble. So we can write that simply copper carbonate is insoluble. Right. That's the answer for that one. Part 2. Explain why polystyrene cup is instead of glass beaker. We just discussed. Polystyrene cup does not let heat from inside to go outside as well as outside heat to come inside, because the reason is polystyrene cup is an insulator. So we can simply write polystyrene cup is a heat insulator. Therefore, less heat is lost to surroundings. So less heat loss is there. So let's see the marking point. Polystyrene cup is an insulator, so less heat is lost. Yes, we have both points, so we get full marks for this question. Now they're asking, give two variables the student should control in the investigation. The common mistake students do in this one, they say that use the same mass of the metal which we are adding. Wrong. The reason is they say that we have to add excess metal, so don't write we have to use the same metal of mass of the metal, but we can use something like this. Concentration of copper sulfate solution should be same. Concentration of copper sulfate solution. That's one point we can write. Then we can say the volume of copper sulfate, because they didn't say the excess copper sulfate, right? So then you can say that volume of copper sulfate. It's only 2 marks. We will only write 2 points, right? What are the other things? We are adding metals, no? So we can say that surface area of the metal, even though you add the different masses, surface area, if you're adding powder of one metal, other metal should be also powder, because the reason is you can't have one is a cube of metal, other one is a powder of metal. No, because we have to have those things constant. And you might have to use the same polystyrene cup, so you can use same polystyrene cup or surface area of metal. We'll write one more. I think we have the 2 points that we need, but I'll write surface area of the metal should be same. So we have to have the same surface area of the metal. Okay, now let's see. Yes, concentration of copper sulfate, volume of copper sulfate, rate of stirring, surface area of the metal, same initial temperatures, same polystyrene cup. We can take any of these points as some answer, so they are only expecting any 2 from these 6 points. Okay, now let's go for next one. Calculate the mean temperature increase for metal Y. They are asking us to find the average. So we have the 3 temperature increase, 6.1, 6.3 and 6. How to find mean temperature increase? This is how we're going to find. So mean temperature increase equals 6.1 plus 6.3 plus 6.0 divided by 3. Our answer is 6.1. Right, mean temperature increases is 6.1. Right, that's how you can answer, because I just wrote the answer only for 1 decimal place. You can see that all the mean temperatures are given for 1 decimal place here. So we get the answer as the 6.1. Explain whether the anomalous result in experiment 2. Okay, experiment 2, there's anomalous result. This is the experiment 2. Where do we have the anomalous results? 4, 2, 4.2. So can you see First reading is 4.0, third reading is 4.2, second reading is 2.0. It's very low, so it can't be. So it has to be there should be some mistake there. Okay. Explain whether the anomalous result in experiment 2 should have been caused by stirring the mixture too quickly. No. First point is no. Why? Because if they stir it too quickly, the rate of the reaction should be faster. So it should be more temperature. It should produce more heat. So the temperature rise should be more higher. It can't be lower. So remember, if we are stirring the mixture faster means the rate of the reaction is high. So therefore temperature should be higher. So we can say that stirring quickly will increase the rate of reaction. Therefore, temperature increase would be higher than what's the value 2.0. Yes, 2.0. It should be higher than 2.0, not like that. So let's see the answer. Yes, all temperature change should be similar, same as experiment 1 or 3. Yes, it should be something 4. Or temperature increase should not be lower than 4. Or in temperature increase should be higher than 2.0. That's what we wrote. As the stirring quickly would increase the rate of the reaction. Yes. So since it's increase the rate of the reaction, temperature should be higher than 2. It should be very close to the 4 as experiment 1 and experiment 3. Right. Explain the order of reactivity for metal W, X, Y, and Z. We know that if the metal is more reactive, it would have higher temperature rise. So I think here we got the averages. I can't remember the exact value. Something 6 point, right? Let's say something 6. Okay, let's say 6 point something. So we can see that higher the reactivity, higher the temperature rise. So we can see that Z shows the highest temperature rise. So that means Z is the most reactive one. Then the second one should be Y. Third one should be W. Last one should be X. Why? Higher temperature increase more reactive the metal. Okay, that's our answer. Let's see. Oh no. Yeah, okay, I haven't taken the mark scheme. I think since it's a straightforward question. Okay, let's move to the next one. Okay, explain why metal X could be silver. Because the reason is, if you take reactivity series, I think you can remember reactivity series. So we have potassium, sodium, so we have more reactive metal. Then we have iron, zinc, iron. Then we have hydrogen, and then we have copper. Below copper there are only 3 metals now. Below copper we have silver. So as I remember, we have silver, gold, platinum. So there are only few metals. Explain why metal X could be silver. Can you see when you add metal X, there was no reaction. What we are where we adding this metal X? We are adding this metal X copper sulfate solution. So if there's no reaction means our metal X should be less reactive than copper. So there are only 3 metals less reactive than copper: silver, gold and platinum. Since there's no reaction, yes, there's a possibility our metal X can be silver. So how are we going to write that one here? So first we say that silver is less reactive than copper. Therefore, there was no reaction between silver and copper sulfate solution. That's the reason. So silver is less reactive, therefore there was no reaction between them. Silver is less reactive than copper, therefore there was no reaction. There was no temperature increase. So no reaction means no temperature increase. That's our answer. Right. Now we came to question number 6. Right. Ethene can be obtained from crude oil using these 2 processes. Okay, crude oil, kerosene, octane and ethene. Give the name of the process 1. Let's see how we get this crude oil and we separate them into this kerosene. This is the thing. The crude oil means something you will find underground. So you can find them. Okay, underground is a mixture of hydrocarbon. Let's take this is we have so this is crude oil, it's underground. So it's just a hydrocarbon mixture. So these are made from like dead organic matter millions of years ago. So what will happen? It has different molecules. It have molecules with 1 carbon atoms. It might have molecules with 2 carbon atoms. It might have molecules with 3 carbon atoms. It might have molecules even with 20 carbon atoms. So likewise, there are long chain hydrocarbons. Then what we do is we drill them. After we drill them, we take this one out. That's what we call it crude oil. Crude oil means it's a mixture of all these molecules. Then we have to separate them based on the size of the molecule, because when the size of the molecule changes, how we can use them, that also changes. Okay, that's what we are going to do is this separation process, we call it fractional distillation. So they are asking to give the name of the process. How do you take crude oil? How do you separate them into gasoline, diesel, kerosene and different fractions? That process we call it fractional distillation. Right, that's the process that you are going to separate kerosene from crude oil. Now they are asking sketch label diagram showing how the kerosene fraction is obtained from crude oil in process 1. Okay, now let's draw it. Okay, so this is what you do. Let's assume here I have crude oil. Okay, here I have crude oil. First what we have to do is you have to heat this crude oil. So here we have crude oil. That's mixture of those molecules, no? So we have crude oil. So here what you are going to do is we are going to heat them. So when you heat them, at the bottom there will be high temperature, like almost close to 400 degrees Celsius. Now what will happen? Most of this crude oil will get vaporized. Then what will happen? So you put them into a column like this. We call this column fractionating column. So likewise there are separate levels. You can take them. I just drew only few, right? Right. So then what will happen? So at the bottom is so hot, like 400 degrees Celsius. So then what will happen? Then in this fractionating column, they have these layers. What they do is they let repeated condensation and evaporation of this paper, which was got heated at the bottom. Now we have crude oil vapor moving through this fractionating column. So when they move in through this fractionating column, this column cools down as it go up. This is a very tall one, so therefore at the bottom, even though it's 400 degrees, when it goes up, at the top is very cold, right? Like 25 degrees Celsius. Okay, there's a temperature decreasing. So when the temperature decreases, in the different levels, different sizes of molecules get condensed. Heaviest molecule will condense at the bottom. We call them bitumen. Bitumen is the one that we use to put like as the to surface of the road. So we call it bitumen, we put it there. Otherwise, some roof in some countries, to insulate roof, we put it them, like put add layers of bitumen to heat insulation, right? That's what will happen. So then we can get different parts, but I'll use separate. So there's another one called fuel oil. Fuel oil, we use it as a fuel for ships. Then we will get diesel. Diesel, you know that for trucks and buses we use diesel, heavy vehicles. And then we get something called kerosene. Kerosene is the one we use it as for aeroplanes as the fuel. So we have kerosene. Then we get the next one, which is well-known one, petrol. Then at the end we will get natural gas, or we call it LP gas, liquid petroleum gas. So it comes out as a gas. What they do is they put it into cylinders, add liquid petroleum and send it to your houses for cooking purpose. So these are the levels. So the different molecules can be separated in different levels, and the weight of this molecule changes. So based on the size of the molecule, it comes. For an example, I'll take a few examples. If you take this bitumen, these molecules have more than 70 carbon, right? You don't need to know that one. It has more than 70. But when you go for like fuel oil, they will have around like 20 to 70 carbons. And if you go to diesel, they have 14 to 20 carbon. When you go for kerosene, they have like 10 to 16 carbon. When you go for petrol, they have 5 to 10 carbon. Then when you go for these gases, they will have 1 to 4 carbon. So likewise, the size when they go up decreases. Sketch a label diagram showing the kerosene fraction is obtained from crude oil in process. Okay, we just draw the tower and we mention that one. How many marks? It's a 5 marks. Yes. Right, let's see the marking scheme. I think we are good. Tower drawn into one entrance and more than one exit. Yes, one entrance, more than one exit. We got the first mark. Crude oil is heated. Yes, heated and vaporized before entering. Yes. Crude oil enters at the bottom. Yes, it enters from the bottom. Kerosene leaves tower but not right at the top. Yes, kerosene is here. Then temperature gradient, 400 at the bottom, 25 degrees at the top. Yes, we get 5 points for this answer. Right. Let's move on to next one. Okay, so we wrote, give two conditions needed for the reaction occurs in process 2. What is this process 2? So we have kerosene, octane and ethene. Our kerosene here, equation is given, right? What is this process 2? So we can see that kerosene has 14 carbon. So now we'll go back to the story that we had. Okay, we have kerosene. Now, what did I tell you? We use kerosene for airplanes, as a fuel for airplanes, right? Okay, we use it for airplanes. Okay, then what I'm going to do is, using this kerosene, I'm going to make octane plus ethene, right? Octane, we know that is 8 carbon. So usually you might also remember, like, they have something called octane number in petrol also. It's a different ratio, but usually if you have this number 6 to 10 carbon atoms, that's the petrol. So these are the ones which we used to pump for cars. Now when you look at the numbers, we know that there are more cars than planes in the world. So therefore there's a high demand for the petrol for cars. But when you take this fractionating column in this crude oil mixture, so the each fraction we get almost equal amount. Because what will happen in million years ago, when these plants and animals die, they don't realize that they have to make more octane or more petrol. So they die and producing each fraction with equal amounts. So therefore what they do is, for practical purposes, we take this kerosene, which is 14 carbon long chain, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and we break it into pieces. So one piece we want to have is a chain with 8 carbon atoms. 1, 2, 3, 4, 5, 6, 7, 8. We want to take this fraction. Why? We want to make this fraction to take petrol for vehicles. This process we call it breaking these long hydrocarbon chains to get shorter ones. We call it cracking process. Give the two conditions needed for this reaction. For this cracking process, we need these are the conditions. So we have to take this long carbon chain and we have to heat it. Do you know the temperature? Yes. Temperature is, you have to maintain 600 to 700 degrees Celsius. 600 to 700 degrees Celsius heating. So we have to heat up to 600 to 700 degrees Celsius, plus there has to be a catalyst. And catalyst of silica. Silica means simply silicon dioxide. And only it's not silica. There's another catalyst. We have to have a mixture of this one. We call it alumina. Al2O3. When you have this catalyst and this temperature, this cracking will take place. Now they ask you to complete the equation for this process. Obviously we know that we have 14 carbon thing. We break it. They say that we get octane. Its formula is given. C8H18 plus ethene. You know what is ethene? Ethene means, it means 2 carbon. Ene means it's an alkene, so 4 hydrogen. How do you know that is 4 hydrogen? Because the general formula of alkene is CnH2n. If the number of carbon atoms is 1, number of hydrogen atoms should be 2. If the number of carbon atom is 2, number of hydrogen should be 2 times 2, which is 4. But here there's issue. Now it's not balanced. Why is that? Here we have 14 carbon. Now we have 8 here. So I have this 8 fraction. How much is remaining? 1, 2, 3, 4, 5, 6. So one molecule should have only 2 carbon. So we'll break 1, 2, 3. We can have 3 pieces of 2 carbon. So therefore to balance the equation, I'll put 3 there. So let's take 14 here. So here 8 carbon, 3 times 2 is 6, 8 plus 6 is 14. Let's see, hydrogen we have 30 here. Here we have 18, 3 times 4 is 12, 18 plus 12 is 30. Yes, it's balanced. So we have the answer. Do we have the marking scheme for this one? I think we don't need. Yes, 600 700 degrees, silica, alumina as a catalyst. Yes, I think it's correct. Explain the use of octane as a fuel. We know it. It used as petrol for vehicles. But they say that 3 marks. So we have to little bit explain that. So we can write octane can be used as petrol for cars, or we can call it vehicles. How it works? It undergoes combustion inside the engine releasing energy. Yeah, from that we can get it. It's 3 marks, but I think our third mark might be here. Let's see. Used as petrol for cars, undergoes combustion, releasing heat or energy. Yes, so we have it. Undergoes combustion, releasing energy. Yes, we got full mark for that one. Using displayed formula, give the equation for the conversion of ethene into polyethylene. That one I'll just explain. This is how we convert ethene into polyethylene. So ethene molecules are like this. These are ethene molecules. We can have large number of ethene molecules. So I'll just take only 3. How they form into polyethylene? What simply happens? Now they have double bonds now. So I just write the 3 molecules here. So what happens? They have double bonds now. So simply what happens? One double bond start moving from here to here, making the link between these 2 molecules like this. And this double bond moves here, making the link between these 2 molecules. This double bond moves here, making the link between this molecule and the next one. The double bond, the previous one, moves here, making the link between these molecules and the previous one. So we had ethene, we formed polyethylene, but remember, this is not even I draw like double bond is shifting like this. It's not a simple mechanism like that, right? Mechanism a little bit complicated, but I'm just telling you the simplest way where you can understand. Now how we can give this one into polyethylene using an equation. So first I'll write, we have ethene molecules. How many ethene molecules? Here I can see 3 ethene molecules. But can we have more? Yes. I don't know how many we have. So I just say we have n number of ethene molecules. Then what happens? It polymerizes. Can you see these parts keep on repeating again and again? Since I use 3 ethene molecules, I get 3 times that same group repeat again and again. What is that part? We call it, that's the repeating unit. Okay, so it's get repeat again and again and again. How many times it will repeat? If you use 3 monomers, you get 3 times. If you use n number of monomers, this will keep on repeat n times. Then now we have the equation. Give the term used to describe ethene in the polymerization process. We just use the word. So that ethene, we call it monomer. Right. Let's see the marking scheme. Yes. Okay, so no need the marking scheme. I think we got that part right. Okay, so with that we finish the first part of the paper, 1C paper. So they have another part, so I'll come back with another video with that section. happy. So if you have any doubts, what you have to simply do is just leave a comment. Thank you.